All right, in this lesson, we're going to be looking at linear and rational equations. At the end of this lesson, we'll be able to solve them and we'll know the difference between the two specifically. So let's start with linear equations. Our purposes will be just focused on those in one variable. And a linear equation, that's an equation that can be written in kind of the standard form that we'll see for that is ax plus b equals 0. So that's kind of the standard form for a linear equation where a and b are real numbers and then x is our variable that we'll be solving for. So just as an example, let's say we had, let's just go 5x minus 2 equals 13. So this is just about the most basic of a linear equation. As you can see, that in this case, that's our a, that's our b, and then x is what we would be solving for. And if we were going to solve this out, it would come, if we add the 2 over, divide by 5, looks like x would be 3 in this case if we were to solve it out to get our solution. So this is just a basic linear equation right here. And another name sometimes used for, not as often, but used for the linear equations, they could also be called a first degree equation because obviously we don't write it in, but we would have, in this equation, we'd have an implied, that's x taken to the first degree. But of course we don't put that in, it's just implied. So another name for it would be a first degree equation. So it's just saying the same thing. And then just to drive home exactly what a linear equation is and isn't, let's just take a look at a few examples here. If we had x squared plus 2x equals 8. So if we had something like this, this would not this would not be a linear equation because we are, in this case, we are squaring the x. If it were just x, not squared, then it would be, but because we're squaring it, that is no longer a linear equation. Or if we had the square root of x, we had something like this again would not be a linear equation because we have a square root involved. And let's take a look at one more example so you guys can see if we had something like that. So in this case, the issue is that the x, our variable, is in the denominator. If it were in the numerator, we would be fine, but because it's in the denominator, that is also not a linear equation. This is more one that we'll get to in the second half when we're looking at the rational equations, but this is not a linear equation because it is in the denominator in this case. And then when you're dealing with linear equations, it's not the best looking one. If you were to graph a linear if you were to graph it, or if you were to be given a set of graphs and you were to need to pick out those which are linear, the key to look for is for linear, you want to look for those. It should come out to a straight line when graphed. So that's a telltale for whether you have a linear equation or not, is the straight line in the graph. So now that we know what a linear equation is and what to look for, let's go through And let's do a couple examples here. Do a couple examples of actually solving them now that we know what a linear equation is. Let's do a couple examples solving. So let's say we had, we'll go 6x minus 4 equals 3x plus 8. So if we were given something like this, clearly a linear equation, there's no variable in a denominator, there's no square root, nothing squared, it's all first degree. So we know this is linear, and now we're actually being asked to solve it and figure out what x is. So our first step would be, we want to combine, get like terms combined. So let's add the 4. Add the 4 over here. So obviously that will cancel this out. We're taking negative 4 plus 4, so that zeroes out for us. So we're just left with 6x on the left equals 3x, and now this is 8 plus 4, so this is now 12. And then we can further combine, now that we've taken care of those without the variable, we can combine like terms on those that have an x. So we can subtract 3x, subtract that over here. And then, of course, this will cancel out, 3 minus 3, so that zeroes out. So now we have 6x minus 3x, so that's 3x equal to, and then we just now have 12 left over here. And then our final step, because essentially what we're trying to do is, we started with combining the like terms, so now we just need to finish isolating x. So all that's left to do is if we divide out the 3, of course do it to both sides, so that cancels out and we are just left with x finally. And then 12 divided by 3, so it looks like 4 is our final answer. So we have x equal to 4. And of course, if you are ever in doubt, you can always check your work and plug it back in. So we're saying that x is equal to 4, so if we go back to the original equation here that we had, so if we take 6 and then times x, which now we're saying is 4, and then minus 4 equals 3, and then times x, which again is 4, so we'll plug that in for x, plus 8. So we have 6 times 4 is 24, minus 4, and then 3 times 4 is 12, plus 8, so it looks like we have 24 minus 4, we have 20, and then that is equal to 12 plus 8, 20 equals 20, so that looks good to me. So x equals 4 is definitely our answer for that one. So now let's do one more on the linear side. Let's do one more example. Let's do just a slightly different one so you can see something a little different at least. So if we take make that equal to, okay. So if we were given this 2 minus, and then in parentheses we have 7x plus 5 equals 13 minus 3x. So now, before we go and start combining like terms, the first thing we want to do is we want to get rid of the parentheses here. So we're going to distribute this negative out here. We're going to take that times the 7x, and then we're going to take it times the 5. So we're going to apply the distributive property here, and we're going to get rid of the parentheses. So we'll still have our 2 here, And then the minus times the 7x will give us a minus 7x. And then if we take the minus times the positive 5, and if it's helpful too, if you think of it like the imaginary 1 right there. So essentially we're taking negative 1 times positive 5, which will come out to negative 5. Negative times a positive will give us a negative. So when we distribute that, that becomes minus 5. And then over here we still have, for right now, we have 13 minus 3x. All right, so now that we got the parentheses cleared out, at least now we can go back to how we started the last one, and let's combine some like terms. So let's just start with the left side, and we can combine the 2 with 5, because those don't have an x variable, so we can combine those like terms. So if we take the 2, and then don't forget the minus here, so we're taking 2 minus 5, which will come out to negative 3, and then we're still minus the 7x, and then this is equal to the 13 minus 3x, okay? And now we can take, and let's do, I think let's add the 7. We'll add the 7x, and then that will clear that out. That cancels out, so we just have negative 3 equals 13, and now we have negative 3 plus 7, which will get us to a positive 4x, and then subtract 13 from both sides, so this is now gone. So we end up with, we'll move over here, so negative 3 minus 13, so that'll get us to negative 16, and that's equal to, all we have left on the right is 4x, okay? And then we just have one more step left to isolate our x. If we divide by 4 on both sides, so we have x equal to negative 16 divided by 4 gives us negative 4 as our final answer. X equals negative 4. And if we go back to this stage here, just note that we could have just as easily, we'd end up getting the same thing if we took instead added 3x, and then we added 13, or added 3. We'd still end up with the same answer, because we'd have 16 on this side, and then we'd have, that would be negative 7 plus 3, negative 4, which would still come out to negative 4. So don't worry about which we chose, why we moved the 7 over. I mean, we could have just as easily, could have easily switched things up. We still would have ended up with the same answer. All that matters is that we were combining like terms and then working to isolate our x variable. So x equals negative 4 for that one. But now let's switch it up a tad. And what if we still dealing with linear equations, but what if we have fractions? So now we're dealing with, still working on linear, but this time we'll do it with fractions. So the key will be to get rid of the fractions. We need to make it easier for us to solve. So we want to get rid of the fractions. And the best way for us to do that will be, call it our LCD. This is our least common denominator. LCD, our least common denominator. This is what's going to be key for us to get rid of the fractions and make it easier to solve. So the least common denominator, the LCD, that's just simply the smallest number that all of our denominators will divide into. So let's use as an example. It'd be best just to see it if we had, and we'll just set that equal to 1/6 plus. All right, so if we had something like this, and we are linear, we have our variables are in the numerators, so we are still linear. So if we were given something like this to solving for x, we want to get rid of the fractions, so we're going to use the LCD. So we have, in this case, we have in our denominators, we have 4, 6, and 3. So what would our LCD be in this case? Well, if we try, I mean, worst case, if it doesn't come to you right away, we can just try, say we tried 8. Well, 4 works, but 6 and 3 don't evenly go into 8. 10, none of them go into evenly, but what if we try 12? Well, 3 and 4, those are factors of 12. Those go in evenly, 6 times 2. So it looks like 12 is going to be our LCD in this case that we're going to use to get rid of our fractions. So we're going to use 12 is going to be our LCD. And now knowing that, let us actually go and solve this. So we had x plus 1 over 4 equals, okay, and our LCD is 12. So now once we have our LCD, what we need to remember is that we need to take it not only times both sides of the equal sign, but it needs to be taken by each part. The x plus 1 over 4, the 2 minus x over 3, and this 1 over 6. It needs to be taken times everything when we're doing our LCD in order to do it properly. So let's start with, and I'm going to do this, try and make this as simple as possible to see. So I'm going to use 12 as a fraction as well. So this is easiest to see. All right, so that's how I'm going to write our LCD. I'm going to write it as 12 over 1, which is just the same thing as saying 12, just in fraction form, and then equal to, and then plus 2 minus x. Okay, so here's our setup now. We have the whole equation set up. We are taking everything times our LCD, which is 12, we decided, just written in fraction form. So now we just got to break up these two fractions because we have not only the x, but we have the 1, just like over here we have the 2, and we have the x. So we need to break those up, and how we can do that is because our denominator is the same, we can just simply take 12. We can split this up into two fractions, adding, but we're splitting it up into two fractions, taking each part times 12. So we take 12 times the x, so we end up with 12x, and then it's over 4. And then the 12 times the 1. Now we're adding. We are adding, so all we're doing is we're splitting up this fraction and just breaking it down into 2. And then we have 12 times 1 is 12, and then we're still over 4, and then equal to. And again, the nice thing about multiplying fractions is, in case you didn't know, multiplying fractions is nice because all we have to do is we can just take the multiply the denominators. So 12 times 1 is 12, and then on the bottom, denominator 6 times 1, we have 6. And then we're going to do the same thing that we did over here. We're going to split this into two fractions. The only difference here will be subtracting. So let's start with, if we take the 12 times the 2, so we have 24 over, we have 3 in our denominator, and now we're subtracting. We are subtracting this time, minus 12 times x, so we have 12x, and then 3 on the bottom. Okay, so let's give ourselves a little more space here. Alright, so this is where we're at right now. Alright, so now we can simplify these. So 12 and 4, which gets 3 plus 12 divided by 4 plus 3 equals 12 divided by 6, just 2. And then we have 24 divided by 3, that's 8. And then minus, just like we did with this one, 12 divided by 3, which is 4. And then we still have the x. So now we did just what we needed to do while we figured out the LCD. We are now able to, we've gotten rid of our fractions and made this into something that is much easier for us to work with and to solve, kind of like we had. Now it's a similar setup to what we had in the first equation, much easier to work with. So now, just like we had done before, we can combine like terms, and let's just start on the right side here. Let's get that combined. So we have 3x plus 3. So we have 10 now, minus 4x. And then, again, just like before, it doesn't, we should come out with the same answer, but I think I'll just add the 4x. Add that over. Okay, so we have 7x plus 3. And then that is now gone. And then if we subtract the 3, we end up with, we have 7x equals 10 minus 3 is 7. And then, let's get a little more room here. Alright, and then our last step, of course, get x isolated, so we just have to divide by 7 to get x by itself. And 7 divided by 7 is simply 1. So after all that, we get an answer of just x equals 1 for that one. Alright, and let's try one more so we can see, get a little more practice with figuring out our least common denominator. Let's do, let's see, we'll do x over 8 plus 5 6 equals 3x over 4. Alright, so now we have, trying to figure out, because we have fractions, so let's figure out an LCD so that we can get rid of those. So we have 8, 6, and 4 in our denominators. So what could we use? What do those all go evenly into? Smallest number. We know 16 would work for 8 and 4, but doesn't work for 6. 20 only works for 4. What if we try 24? That's 8 times 3, 6 times 6 and 4 are factors, so it looks like in this case 24 is going to be our LCD. So just like we did before, after we got our LCD figured out, we're going to take, and I'm going to do the same thing as we did in the last one, just so we can see it clearly. So we're going to take both sides and each part by 24. I'm going to write it in fraction form. And equal to, okay. Alright, so we're taking everything times the LCD, and this will allow us to get rid of the fractions. So at least this time we don't have anything to split up, any fractions to split up, so we're just multiplying straight across numerator and denominator. So x times 24. So we have 24x divided by 8, and then do a little math here. So we have 5 times 24. That will come out to 120 over 6 equals 3 times 24, so we have 72. Don't forget the x over 4. Okay? And now let's do some division and get rid of the fractions once and for all. So we have 24 divided by 8, so that's 3x plus 120 divided by 6, that is 20. And then 72 divided by 4, that comes out to 18. And then let's combine our like terms, so, and we just have the number with the x variable to worry about, so minus 3x minus 3x. So we end up with, so we'll just have 20 left over on the left side. And then 18x minus 3x will get us 15x. And just like we've been doing, to isolate x, we just divide by 15 on both sides. So this is now gone, and we just have x left over, and then we have over here, we end up with a fraction, 20 over 15, which would be our final answer, but if they wanted us to, and we will do that, we can simplify that fraction. So we can take, we can take 5 out of both 20 and 15, so if we divide the top and the bottom by 5, that would get us to 4, and then 15 divided by 5, 3. This looks like our final answer, simplified. We have x equals 4/3 as our final answer for that one. So now let's shift over to, now that we've seen linear equations and we know what to look for, let's shift over to the other part of our lesson. Let's look at now rational equations. And these are equations that contain one or more rational expressions. Now, if you're asking, well, what is a rational expression? That's a fraction where both the numerator and the denominator are polynomials. That's all a rational expression is. So, for an example, we could have x plus 3 over x minus 2, maybe. All right, so we have a polynomial in both the numerator and the denominator. So we have a rational expression here, and then all a rational equation does is it contains one or more of these rational expressions. Let's see, one more. If we had x squared, it's 2x plus 7 over x minus 3. Again, this would be a rational expression, which we'd see in our rational equations. We have a polynomial in the numerator and in the denominator. And the key difference between what we had been working with the linear equations is that these equations will have variables in the denominator. So we have to make sure that we avoid any values of the denominator that would make, or any values of the variable, sorry, that would make the denominator 0, because we can't divide by 0, because that would make it undefined. So with rational, by having a variable in the denominator just kind of adds an extra step for us. We have to be mindful of any value of x, like say in this case, if x were 3, we just have to be mindful of anything that would make the denominator go to 0, because that would not be included in our solution set. So let's take, be best just to see and get right into a couple examples. So let's do a couple rational equations. Let's do, okay. So if we were given something like this, so we look at it, we see, okay, well, we have our x variable. I mean, we have it in the numerator, but we also have it in the denominator. So this is definitely going to be a rational equation. So the very first thing that we want to do before we even start solving this is we want to figure out what x can be. We need to figure out what makes our denominator 0. We're trying to, basically just trying to identify our domain, which the domain is just simply, it's the set of real numbers that the variable is permitted to have. That's our domain. So let's start with here, well, this one makes it easy for us in this one because our denominator is the same. It's x minus 3 in both. So we only have that to worry about. So so we have x minus 3 and set it equal to 0. Okay. And then all you're doing then, we're just solving, add 3, and then, so it looks like x equals 3. If we have x equal to 3, we'd have 0 here, just like we'd have 0 here, and we cannot divide by 0 because that would make it undefined. That's a no-go. So by doing the domain first, figuring out what makes the denominator 0, now we're mindful of when we solve this, if we were to get this for our answer, we can be like, all right, no, that does not work. X cannot be 3. And if we wanted to see this, if you were asked to write out what the actual domain is, you could many times you'll see it's something, usually written something like this, where we have, and then that means that x cannot be equal to. So you might see it written something like that, which is basically just saying that our domain is all real numbers except 3, everything but 3. Any other real number in there and we'll be fine, just not 3, because that'll get us 0 in the denominator. So now knowing that, once we've taken care of that first step, now we can actually go about solving this. So we'll figure out just like we did with the previous ones when we had fractions. Let's get our LCD. Okay. And again, this one's not too bad because our LCD is just going to be x minus 3. And don't let it confuse you just because it's not just a standard number. Don't let it confuse you. All we're trying to do is we're using the LCD to clear out the fractions. And when we multiply everything out, our x minus 3, which we'll have up here, that'll cancel out with what's in the denominator. So let's see it written out so it's easier to visualize. So our LCD is x minus 3. So and then we have that equal to, and let's clear some of this out. Okay. And then minus, again, you have to take the LCD times everything. Okay. So now it's a little easier to visualize how this is our LCD and we can use it to clear out the fractions. Because now when we do this, when we take this times this, we have an x minus 3 in the numerator and the denominator, so they will cancel each other out, which just leaves us with, now we just have 3 over 1, which is just 3. And now here, again, we have an x minus 3 in the numerator and the denominator, one in the top and the bottom, so they will cancel each other out, and we're just left with x and 1, x over 1, which is just x, and then minus, in this case, again, I kind of wrote it like, if it's helpful to visualize it, so in this case, we don't have cancellation, but all we're doing is multiplying fractions, so let's multiply the top out. So we have 3 times x, we have 3x, and then we have a negative 3 times a negative 3. So a negative times a negative will get us a positive. So we'll have positive 9. And then obviously it's just divided by 1, so we're good there. So we have 3 equals x minus 3x plus 9. So let's combine some like terms here. Okay, these both have an x variable. So let's combine that. So we have x minus 3x. And if it's helpful, remember imaginary 1 here. So 1 minus 3 is negative 2. And then x plus 9. And now we can take and we will subtract that 9 over. All right, so that cancels out, and 3 minus 9 will get us to negative 6, and then negative 2x. And we can isolate the x, final step, divide by negative 2, divide by negative 2. So we have x equal to negative 6 divided by negative 2, so we'll have a positive. Looks like a positive 3. But is that actually our solution? And see, that's why we wanted to go through and do, so we can see it again, we wanted to go through and do the domain first. Because if we recall, when we did that, we said that x cannot be 3. Because that would get us 0 in the denominator. X cannot be 3. So that's why I say it's better to do that first, because otherwise, if you don't do that, then some people, they'll just go right into solving, and then they'll get to here, and they'll be like, okay, well, boom, the answer is x equals 3. And then they forget that, oh yeah, I gotta check it. You know, says some people might forget to check it, go back and check it in the original equation. But in our case, it's helpful for me to see, like, okay, I did, in the first step, I did the domain, and I wrote out exactly what it cannot be. X cannot be 3. So, as it turns out, because x cannot be 3, then our actual answer is that there is no solution in this case. So that will be our final answer, not the x equals 3. There is no solution in this case. And finally, I did just want to briefly touch on, since we've been working on solving algebraic expressions, I just want to briefly go over 3 different types of equations. So the first one called an identity. And an identity is just an equation that is true for all real numbers. So if we had, as an example, let's say you had x plus 5 equal to x plus 2 plus 3. Well, if we combine like terms over here, we end up with x plus 5 equals x plus 5. We end up with the same thing on both sides. So in this case, our solution set includes all real numbers. It doesn't matter what we put in. For x, we're going to get the same thing. We'll do one more example of that. If we had I think you can see where this one is going. If we distribute, get rid of the parentheses, we end up with 2x plus 6 equals 2x plus 6. We have the same thing on both sides. Doesn't matter what we put in for x, we will still end up with the exact same thing. So an identity is an equation that it would be true for all real numbers. Whatever we put in for x, this will be true. And the second one that we're going to look at is the conditional, called a conditional equation. And for an equation like this, it's only true under certain conditions. It'll be true for at least one real number. So let's say we had 9x plus 7 equals 34. Well, if we solve this out, minus 7 both sides, so we have 9x equals 27, and divide out 9. And we're simply left with x equal to 3. So we came out with one answer in our solution set, one answer that works for this particular equation. So this would be a conditional, because we can't, unlike an identity, I mean, we can't just put any old number in here and have it work. In this case, there's only one solution that works. So this is a conditional. And I mean, we would specify there, it doesn't have to be. You could have 2, 3, 4 different answers in your solution set. But the difference is that it's not an identity, it's not any real number, it's that there's at least one, just not an infinite number of solutions when we're talking about a conditional. But more often than not, you would see that, as something where we just have an x equals to one answer in our solution set. That's a conditional equation for us. And then the final one is what we would call an inconsistent. And that's an equation that is never true, regardless of what we put in. So if we had something like this, well, it doesn't matter what we put in for x, it'll never be true by virtue of, on the right side, we're adding 5 each time. So whatever we put in for x, this side is going to be 5 greater. So this one will never be true. So this is an inconsistent equation. So we go from the identity, where all real numbers will work, to the conditional, where there's at least one. There could be more, but there's at least one, but not an infinite amount. And then finally to the inconsistent here, where it's never true. It doesn't matter what we put in. So we would say this would just be a no solution one, because we wouldn't be able to solve for x in this case. All right, so to summarize things up, to give kind of a broad overview of the main differences to remember what we covered here, if we're looking at the difference between linear and rational. So remember, linear, kind of have our standard form, ax plus b equals 0. Again, a and b are real numbers, x is our variable that we're solving for. And this is, of course, this is in one variable, which is just what we're focused on right now. So linear, we look for it in a form like this. If we were to graph it, we would see a straight line when we graph it. And for our domain, we'd be looking at all real numbers. We don't have, unlike with the rational equations and the denominators, we wouldn't have restrictions. All real numbers would work. So we don't have to worry about, with just a basic linear equation, we wouldn't have to worry about checking for a domain. And then, contrast to the rational, we have the variable in the denominator. That's a no. Variable in the denominator. Okay. And then we have to exclude values that make the denominator 0. So we end up with, call it domain restrictions. And like I had said, do that if you get one, if you get a rational one, and you have the variable in the denominator, figure out, set the denominator equal to 0 first, figure out what x cannot be before you proceed into solving. So you don't get to the end and be like, oh, this is the answer. Because if you're gonna do that, make sure you, which is the last point I was gonna make on the rational side, if you're not gonna check what the domain can't be in the first step, then you need to absolutely remember that answers must be checked. Answers must be checked so you don't get something that makes it undefined with 0 in the denominator. So that's our main differences that we definitely need to remember between linear and rational equations. All right, so that does it for this lesson. Hope it was helpful, and thank you for watching. Be sure to check out the channel for more algebra lessons.